very nice and considerate. Like other people. I will not say names.
Like, who's missing your own?
I guess we should start, huh? So we don't go late. I'm sure you're super excited. Numerical relativity in the morning. Nothing better. Clearly switch from bored because I don't think I can do it. We'd be here all day writing down equations that there's an awful lot of equations in this, and none of them are something I think you should be scribbling down, right? It's just to introduce you to what it looks like. I don't know how many of you are really interested in numerical relativity, so this is just to give you a sense for what we're actually doing to solve Einstein's equations. So when we have the events that we've had from the gravitational wave detector, so far they've all been mergers of black holes. And because of the masses of these black holes, and they're a little bit massive, right, compared to neutron stars especially, that means they're merging right in the sweet spot of LIGO. So that means that the nonlinear aspects that we want to know, we need to use Einstein's equations in their full complexity, is all right there at the highest SNR, signal-to-noise ratio in band. So that's why we're spending a lot of time making sure we do the correct solutions to Einstein's equations to get all that right. And then, of course, people also model these solutions using the numerical relativity waveforms to create models, and I'll talk a little bit about that tomorrow, although not in any great detail. So this is just one of the methods we use to get at the full signal. So this is the part we need for the merger. Can you see that? It's a little hard, isn't it? It's kind of tiny. But this is just to get us started on what numerical relativity is. I've been using this joke for a long time, so some of you will have heard it. Back in 1957 was the first known mention of someone trying to define how we were going to solve Einstein's equations, since they are, as we vaguely saw yesterday, not in any real way, but they're nonlinear, and there are a lot of them. And the problem is that they're so complex that you really can't solve Einstein's equations on a piece of paper, not even for the two-body problem, which would be so trivial in Newtonian physics, right? But because it's nonlinear, we can't just superpose. I hope someone's going to be okay. They're going to the hospital. You can't superpose two Schwarzschild solutions and come out with a binary black hole solution. So this is why we end up needing to use computers. So Charlie Misner. Anyone met Charlie Misner? Only the old people? Anyway, he's awesome. Have you met him, Dan? He's awesome. I just saw him 2 weeks ago. He's still alive. He said in 1957, right? I just wanted to point out he's still alive. First, you assume that we have a computing machine. That's one of my favorites. Computing machine better than anything we have now, and many programmers own lots of money, so some things never change. And so we're going to solve what we're going to talk about today. So general relativity becomes an initial value problem. If you want to solve something on a computer, we know how to solve things like the wave equation. So what we're going to do is we're going to recast Einstein equations as best we can into something we can solve, which is initial value problem. And he's saying once you specify the initial conditions, either the programmer will shoot himself or the machine will blow up. And that's where we were. And this is true for like the next 30 years. No one died. But I think we came close. I know I was depressed in grad school. Because it's very, very hard to solve even something as trivial as the two-body problem in vacuum general relativity. We don't even have a right-hand side to the equations, and it was still very hard to solve. So in 1985, I think Saul Tokoski has since told me, never call a problem the Holy Grail, because you know you're dooming yourself. Like, it's a dumb thing to do. But Stu Shapiro and Saul Tokoski in 1985, it was the beginning of the real push, because people felt the computers had gotten good enough, although they hadn't, to call the Holy Grail of numerical relativity a code that simultaneously avoids singularities, handles black holes, maintains high accuracy, and runs forever. And now we would add, please do that faster. Because it's slow and there's a lot of information we want. So that's where we were. And I won't talk about the things, the breakthroughs today, because I'm just going to go around background. I'll talk about it tomorrow. But famously in 2005, Franz Pretorius was the first one to actually collide two black holes stably and get out and do it without crashing the code. So that's where we are. Now we have this capability. And in fact, it's at the point where if you were really brave, there's a public code available, the Einstein Toolkit, and you could go download it and spend, it is true, about 3 days compiling. I will be honest. So that is why one of your assignments was not to download the Einstein Toolkit and run a binary black hole simulation, because it takes a long time. So if you are really interested in doing this, none of your projects for the next 6 weeks have numerical relativity in it, but the Einstein Toolkit community runs workshops where you can learn how to run the code and they will help you. And there's also an online community that will help you solve your problems as you try to compile and run the code. So if you're interested, you can do it without sitting in one of the major groups. You just need help.
Or you can go visit Georgia Tech.
You can come visit me. It has happened. People have shown up, and I'm like, oh dear, let me see what postdoc or students are around. And I run away. Because I don't remember how to do it anymore. Okay. So what we're going to do, and you can tell me to slow down, everybody's final exam in a foreign language. I'm aware that I speak very quickly, and I don't enunciate. So we're going to start with oh, I forgot the fun pointer. We're going to start with where we were yesterday. G mu nu equals 0. Again, I'm never even going to mention the right-hand side because we won't need it for black holes. So this beautiful equation that had all these lovely properties, we have to go from there to one of these waveforms that we've seen so much of recently. And the question is, how does that happen? Okay. And so what we have to do is take away, we spent all this time in general relativity. Like, I even scoff if I read a paper or a book that says space and time, right? We're really snotty. It has to be space-time, like that's some magical, connotation. But the first thing we do in numerical relativity is break that apart again and go back to space plus time. So 3 plus 1, which you'll hear a lot, just means 3 spatial dimensions and 1 temporal dimension. And it means that in order to solve the problem with methods we know how to use, that have been built from fluid dynamics and E&M and all these other things, we're going to take this beautiful space-time and think of it like a movie. So we're going to have 3D slices of space, and we're going to evolve them forward in time. Now the problem really is there's an infinite way to do that. And this really was one of the problems for many, many, many years because you have so much freedom, gauge and coordinate, that we get to define what we mean by space and time, and that causes a lot of problems, but we've overcome those, so now there's basically a prescription. More than one prescription, in fact. So what we're going to do is we're going to make an initial and boundary value problem, so we're going to specify initial data, and then Einstein's equations are going to evolve those forward in time for us, and then we're going to have to specify some boundary. So if you want to solve the two-body problem, you're going to have to figure out how to specify the initial data for 2 black holes that are doing something you want, and then solve forward. So that's our procedure. Everything else is just details. We really could end there. That is what numerical does. Thank you very much. It's going to rain today, but let's go at it. Okay. So there's so much, like, you can't. And in fact, this is something I don't teach, which is why all of a sudden it's become on a Beamer slide instead of on the board. I don't teach a class in numerical relativity. It's almost more like apprenticeships. We hand it down very archaically, how you do this. But there's an awful lot of, we can write down what we say we do, but if you sat there with us in the codes, there's an awful lot of finagling. There's a lot of art in it as well. So this is just as best as we can say. And I obviously can't talk about all this, and we could keep going on. So I just picked a few. I tried to give a most general as I can overview of all of it. And I'll try to point out the places where the trickiness is, so you know where to pay attention to what we might do wrong. As we say, we always say we do everything right in numerical relativity, because the joke is, in my mind, that if you do neutron stars, you could be wrong, right? There's so much physics we don't know neutron stars. But if you're going to study black holes with numerical relativity, then literally the only mistake we can make is how well we discretize our equations to solve them on a computer, and how well we specify initial data. But we're not having any missing physics, and so in that sense, this is a very luxurious place to work, because we're not scratching our head over neutrino transport and all this other stuff. So we really are just straightforward solving what Einstein gave us. We can also solve alternate theories of gravity, and we can talk about that if anyone's interested. It's just harder. There's so many ways. No one's interested. Everyone's like, no, we believe in Einstein. Okay. This is what we start to get icky, because the problem here is going to be that you have to introduce so much jargon just to describe what we're doing. So because we have to split up this beautiful 4-dimensional space-time into what we call foliations or hypersurfaces, I don't know why we always make the language so hoity-toity, but that's what we do. So we're going to take this space-time and we're going to make it into a family of space-like three-dimensional hypersurfaces, and we usually label them as sigma. So each one of these is a 3D slab of space. And then we have to figure out what a good time dimension would be. And by a good time dimension, I mean we're going to have to solve this numerically. So everything has to be done in such a way that little tiny errors, which numerical errors always exist, will not cause you to get infinitely bad. We have to be stable. So every choice is very carefully done. But the language I have to introduce is we're going to call the function that describes how we slice up in time, we call lapse. And the shift, beta, it determines where the coordinates are in each spatial slice. So that you have a prescription going from one point here to one point in the next hypersurface. So this is the art of numerical relativity, is really in specifying these conditions, the lapse and the shift. In fact, people have spent their whole career coming up with these things. Not me, but other people. Miguel did this for a while. Where's my Miguel fan? Yeah. So actually, one of the coordinates we still use are pretty much Miguel's coordinates up here. So alpha determines how much proper time has elapsed between the time slices according to some normal vector n, which we'll always use, and beta determines how much the spatial coordinates were shifted in sort of a basic physical intuition way. All right, so we got our little normal vector, and now our goal is we have to define things on that hypersurface, right? We have our new three-dimensional space slice, so we need a new metric that's, projected onto that hypersurface. So instead of having the G we've come to know, and all of a sudden everything's A and B, because we're talking about spatial slices instead of four-dimensional space-time. So, I don't know if that's true here, but anyway. So what we're going to do is we're going to make a new metric that's only defined on the spatial slice, gamma, and he's just going to be the projection of the big metric along these normals. And then what you get for free is something called the extrinsic curvature. So extrinsic curvature is basically, there's a lot of ways to think of it. But what it is the measure of how the hypersurface is bent with respect to the four-dimensional spacetime. So since you took a curved 4D spacetime and you broke it down into these slices, we have to understand how we've introduced a curvature within that foliation. And that curvature within the foliation is the extrinsic curvature. You can think of it like that. You can think of it as sort of a velocity term for the spatial metric. There's a lot of ways to think of it. But basically, when you combine lapse, shift, extrinsic curvature, and the spatial metric, you come back to your 4D space-time metric. So these are all the new pieces that get introduced merely because you want to solve an initial value problem. It is kind of a bugger. The other problem is that now we need a whole new set of derivatives. So we spent all the time in general relativity being very careful about how the heck do you invent derivatives when you can't move your vectors around in curved space. And now we have to do the same thing on all these spatial slices. So we have to define what it means to take spatial derivatives, and then we have to define what it means to take temporal derivatives so we can evolve forward in time. So this, fortunately, is pretty mathematically straightforward. Once you've defined what you mean by time and space, then all we're doing is basically projecting our original fancy covariant derivatives, Lie derivatives, etc., onto these new vectors, basically. So I really skip most of this because it's just a lot of equations that look like this. It's like a bunch of spatial metrics multiplying our original types of derivatives, like this covariant one. This is the most popular, this capital D. This is the, what we use is just the spatial projection of the covariant derivative. So everywhere we would have had a derivative, like normally in Newtonian physics, became a covariant derivative in general relativity, becomes a capital D. So as long as you don't worry about it, then it's not, we just have a prescription for that. So the space, and all of the properties we had before will still be true. So this new spatial covariant derivative of the spatial metric is still 0. So we're inheriting everything. Yes?
So that statement that you just made, that the spatial covariant derivative of the spatial metric is 0, means it commutes with all the 3D derivatives. But you have chosen, when you're talking about how to define things, to do the derivative of 4D first, get the combined tensorial object, and then project it down.
Yes.
Gamma doesn't commute with
You have to check.
parabola, the 4D thing.
Does gamma not compete with the covariant? No, I don't think so.
Yeah, so
I haven't done it in a long time, but I don't think so.
Okay, so that's an arbitrary choice that, you could have made something different.
Oh, yeah. And this is really the problem. You could do a lot of things. This is pretty standard. I don't think,
I guess if you'd done it differently, you wouldn't get it compatible.
right. I mean, you really need that compatibility at the end of the day. But there is an awful lot of things you can do differently, but I don't know of anybody who actually makes different choices than these. I think this is too nice of a property we want to preserve, so most people make this decision. I can't think of anything else. 3 plus 1, this is certainly true, that we do this. There are other approaches, so you don't have to do 3 plus 1.
But for your time step, that's the way to do it.
Yes.
Because
Otherwise, what would you do? You'd be a mess, yeah. So this is all very
You have
standard.
The time is special. Yeah.
Mm-hmm. And we've had to spend, I suppressed this, although they might be in my original notes because they were too long. I don't know if anyone noticed how thick that packet would have been. I had a lot of information originally on how you define a time direction so that you're going to be able to have nice properties. So there's a lot of, when people talk about the fact that they're studying formulations, there's a lot of decisions you have to make so that you can, you need to be able, if you're going to take a derivative in time, what we call time has been carefully constructed to be orthogonal, is something good, and all these nice properties happen. So these, I haven't talked about that because, I mean, we could spend all day talking about it, but it would be really boring. But when I write all these n's and t's, everything's been very carefully constructed to have good properties for when we take derivatives. Orthogonal to things we want them to be, and everything's well. Actually, it turns out that this whole procedure is not what we use, 3 plus 1. It's horrible. And it is the reason why codes crash for 20 years. So it's the simplest, but it's not what we do. But there's no one in their right mind would teach you what we actually use is usually BSSN formulation, and it just makes everything look more complicated. So it's easier to learn it here and then find out, oh, you made these adjustments and now things work. So we won't, I'll show you BSSN, but this is the way to understand sort of the procedure. And then, of course, there's all these nuances that would trip you up. I've almost forgotten most of them. It's all I used to think about, and now it's been forever. It's amazing what success does. Who cares? Just run the code.
You still use 3 plus 1.
We use 3 plus 1, not ADM.
Yeah.
So this is the ADM formulation is what I'm showing you right now. And it's the most obvious choice since the first thing that was done by Arnwet, oh, I've forgotten, and Misner. And I don't remember the D right now. Thank you. I'm glad someone's paying attention. So this was the standard that I grew up with. And then finally, Baumgart, Shapiro, Shibata, Nakamura, and 2 other people adjusted it so things would be better posed. So the problem is that in the ADM formulation, if you have a little truncation error, which is inevitable, you blow up. So you're supposed to, yes. I like
Maybe
this.
you get this. It's sort of a historical question. Why is it BSSN instead of SNBS?
So it should totally be SNBS. In fact, it's arguably SNOKBS.
Yeah.
But I don't remember. I mean, someone named it, and I don't think that person was not Baumgart, and that person was not Shibata Nakamura. But unfortunately, the first person who wrote down the abbreviation just did BSSN, and it was such an easy thing to remember. It became historic, but it wasn't. It was that Baumgart really popularized the method.
Is there a single paper that has the authors in that order or anything?
No, because Shibata Nakamura and 2 other people did it first. No one noticed. It's one of these. Like, not very many people noticed. Baumgart and Shapiro did it again, and then people realized, oh, it's really this effort of a combined group of people. So it's just that I remember the first talk that Baumgart introduced these coordinates in Texas. I was a grad student. I was like, Richard, my advisor, we should do that. He's like, don't be stupid, George. I'm like, stupid. Who was stupid? I was, but I didn't push. Damn it. Anyway, we never would have been able to do it. So in the end, despite how much better, now Franz Pretorius used a completely different set of foliations than this. He did not use BSSN. But again, I'm just choosing the most popular thing to talk about. But it isn't just the formulation of the equations. As important as all that is, because if you had the best computer but crappy formulation, you would still not be able to evolve. I strongly contend that even if as a grad student I had convinced my advisor, or we're smart, and this is what you should always do, is go do it yourself, and why are you asking permission? Anyway.
Don't listen to your advice.
Don't listen to your advisor. Prove to him he's wrong by showing him that that's exactly what you do. But I was so silly. But our computers weren't good enough. So if you actually look back at what we were doing, we weren't resolving the problem either. So we like to make this breakthrough myth that, you know, someone had magically come up with these formulations, and it's not true. People have been using BSSN for a very long time, actually, by then, and even had in place a lot of the gauge conditions, modulo some details, but we weren't resolving enough. So even if you had used the magic combination that worked in the end, you still would have crashed because you didn't have enough resolution over those black holes. So we really needed better computers, is the truth, combined with these formulations. All right, where are we? 3 + 1 splitting. Oh, yeah. So this is what I was saying, that what you get back is this space-time metric that we were talking about yesterday. And in this formulation, so there's all these different choices. You could do 2 + 2 and do some kind of null stuff. You could do 1 + 30. Just kidding. It's the same. You could do lots of different choices. In this decision, this is how you would reconstruct the space-time metric. So what you've done is your 0, 0 component is a combination of these lapses and shifts of how you move your coordinates. And here's our spatial metric, gamma ij, which is the one we're going to be solving for mostly. And also you'd have the extrinsic curvature. So we have to build the extrinsic curvature out of these things. So what we end up with, if we were talking about electromagnetism, it would be the same thing. What we've done is we've taken our equations. Now we have evolution equations, and we also have constraints, just like in electromagnetism. So we're going to have a set of equations which are defined on each spatial hypersurface with no time derivatives. Those are constraints. And we're going to have a set which relates everything between adjacent hypersurfaces. Those are evolution equations. And so that's where we spend our time. Well, God, now I'm having flashbacks. So
It's all over now.
it's like, just breathe through it. You're a full professor. Something worked. I don't know. But boy, that was some dark years. Okay, so the Hamiltonian momentum constraints, I'm writing them up here. I'm not expecting you to be, oh, thank you, that really explains things, just so you see what they look like. They're elliptic equations. They don't have any time derivatives in them. So that means, the magic of this means that if I satisfy them once on one hypersurface, which will be our initial data, then they should be satisfied forever. And so all we do is monitor them. We check how well are we doing. The problem with constraint equations is, what does it mean to remain zero? That's notoriously ill-defined, right? Is 10 to the minus 23 zero? Yeah, I'm happy with below, round-off error. But they can grow, and so actually I haven't looked at a constraint output in probably 8 years, but we used to monitor these all the time to see how things were happening. In fact, one of the tricks for Franz Pretorius was using the constraint equations and replacing some of the bits of the evolution equations to ensure that he was keeping things from growing. He was using them to damp out any growing problems with the evolution equations. So you can also be very tricky. There's a lot of tricks in this. So I kept rho and j here, which would be like densities and charges, even though they're zero in vacuum solutions, so that when we look at this from E&M, they will look more familiar, just to give you something to look at. Anything without indices means we've taken the trace. So you just think of, we got rid of all the indices by using the metric. Same thing with our extrinsic curvature. And here's our new derivatives on the spatial slice. So the hard part is that these look nice and innocent, but they're elliptic equations, which are hard to solve, right? Especially, the thing that's always floating around everywhere here is we have 2 black holes in here. How many computers like it when you have something infinite hanging out in your code? None of them do. So that's really the whole thing that's different from the neutron star world and the black hole world, is that in the end we have to deal with these singularities sitting around. And in fact, neutron star people do too, because once they collide, there are 2 neutron stars, they often end up with a black hole. And that's the tricky part as well. So we have to solve these equations for 2 singularities in there, and they're elliptic, so they're slow, so people don't do it very often. And then you can check to make sure they're maintained in time. So it's a necessary and sufficient integrability condition. Just so you know, everything is correct. This is what they look like all together. The famous, don't tell those guys, you know, at least I remembered Misner. He's the only one you could tell, but I can't remember their names. This is the ADM formulation in 3 + 1 coordinates. So now we have a set of equations. This is one equation. There's no indices left. This one is 3 equations, so we have 4 constraint equations. Here's our evolution equations for the spatial metric. You see this T here, and all of a sudden there's this fabulous Lie derivative along the shift. I haven't described those at all. Lie derivatives are basically directional derivatives, fancy directional derivatives generalized to curved spacetime. So here's a bunch of equations, and here's a bunch more. And if you look at them, this guy is the one that's tricky. You have our Ricci, which you might remember is built off of Riemann. So all of this is a bunch of second derivatives of the metric, Christoffel symbols and all that. So if you dug down deep enough into our codes, if you dug really deep, the thing that takes the most time, not including like special things like elliptic equations, is really solving for all these Christoffel symbols and Ricci tensors, because it's a bunch of derivatives. So that's where people spend a lot of time making codes faster and stuff like that, because it's just a lot of time to solve. So the beautiful thing of this is what you've done is everything here on the right-hand side is spatial. So we've managed to say, everywhere I step in time, I'm now going to solve spatial derivatives, and then I'm going to move forward again. It complicates these derivatives on the left-hand side are kind of complicated. But in the end, we actually can use something called method of lines. Has anyone taken a computational class? Now you're all like, what's a computer? And I should say, we don't use Python or MATLAB to do this. As much as I love Python, I hate MATLAB. So all this stuff is it takes anywhere from a couple weeks to a month to run one choice of initial data in a 2-body problem of numerical relativity. It's even harder to do, you need more memory to solve neutron stars. You just have more things to keep track of. So everything takes so long that every decision you have to make as you build these codes is, well, all right, is it right? And is it going to be fast? So there's not one language. It's not a beautiful, most of these codes aren't beautiful. There might even be some assembly somewhere if you dig deep down to make everything faster. So it's definitely a challenging thing. Today, for the most part, and the groups I work with that all do Einstein Toolkit-esque BSSN type stuff, we use Mathematica to code the equations. Mathematica generates the evolution equations for us, so there aren't any mistakes, and we move forward. Okay, so that's how we usually do. We have Mathematica to check the equations, and then we've generated the code. You don't often change the formulations anymore, right? So I'm not usually in here. I used to when I was a postdoc or grad student. We were changing these all the time. Now it's pretty set, so we're not usually coding at that level anymore. But if you wanted to do an alternate theory, if you wanted to change something, it's relatively straightforward to regenerate the code to do that. So the hard part is really coming up with a reason why you're going to choose a certain equation, not actually writing the code to do it.
So is your time step mainly constrained by the evolution equation? That's it.
What do you mean your time step? Like how big it is?
Yeah.
Yeah. So part of the problem is that you're also constrained. So I didn't even put this in. I suppressed a lot of the numerics, and that might be a mistake. So bring it up when you think about it. So right now, depending on how you solve all these spatial derivatives, so I'm going to use finite differencing. You could use spectral methods or whatever you want, but the problem is going to be that there's a certain stability condition in which I can't take too big of a time step based on how small my spatial steps are. So you're there's a tension, you're stuck a little bit. Our other problem, so that's one of the key problems, how big of a time step you can take is based on these decisions you've made spatially. And the other is, we're putting the universe in a box, okay? And that's not right. And so gravitational radiation is defined as radiation at spatial and temporal infinity, which I'll talk about in a second. And yet we sit in a box. Some groups will do spherical coordinates, that's details, right? So you sit in a box. I have 2 black holes with a singularity, which is a bugger, because I have to resolve that well enough that things don't blow up in my face. Then I have to solve outgoing radiation. So the real tension in numerical relativity is you need enough resolution for these holes, and also enough to just, I've got a wave coming out, and I need to resolve that wave with enough points. So even though we use adaptive mesh refinement, we can never get away with murder like someone who's really only talking about following something flowing could forget information in some places of the grid. We can't do that because we have to follow that whole shell of outgoing gravitation radiation. So this is really our attention and why we don't scale well. Like if you threw me more and more processors, at some point I won't gain anything in a single run because I have this tension that I have to resolve this and that at the same time. And this is going out to infinity. So I have to also decide when I'm going to call it. I'm going to say this is now far enough away that I still can resolve it well and see its radiation. And I'm going to say I understand that it's actually, at this point, outgoing gravitational radiation. So a lot of these decisions, we don't talk about it so much anymore, but because since there's really two big code bases, there's many codes. But you have the people who are doing something that looks like what I'm talking about, and the people who are using like spectral methods and different codes. Usually they call themselves the SXS collaboration. I really wish it was something else. It's hard to say. Tell them I said that again. That are so different, and then when we compare our radiation that it agrees is a lot of confidence building. Because we've all made different choices, and actually none of them seem to really matter that much. So you just have to figure out how.
But is the ultimate waveform depending on your computational domain, and you have to make sure that you converge to the right
Yeah.
condition?
Yep. So there's a lot of things that will affect the quality of that waveform. One of them is the biggest one is the resolution of the black holes. Then the next one will be how well resolved were you at the moment you pulled that radiation from your grid. But the hidden issue, like if I showed you those constraints and plotted them, you would see my grid. You would see all my mesh refinement boundaries. So every time outgoing radiation hits a boundary, you get a little effect. And then you have to make sure that your resolution is high enough that you will never get rid of those things, right? But they have to be low enough that it doesn't impact the gravitational wave quality. And you'll also get reflections off the boundary because there shouldn't be a boundary, and you put on boundary conditions, which I'm actually not going to talk about, but and you get those reflections coming back. So all of that is true, and then there's also initial data stuff I'll talk about in a second. So that part is really ugly. If you actually looked very closely at stuff, you'll see all the imperfections of this.
Maybe this is really stupid. You keep talking about how you need to resolve the singularity well. If there's no information propagation out to the event horizon, how can the singularity affect what you see at infinity?
It's because non-physical modes propagate out. So physically, no information leaves the horizon. Computationally, it can. Right?
Especially with a steep gradient.
Yeah. And so, unfortunately, once you're doing computational methods, this world of the beauty of that thought, which is completely true, and I'll talk about that in a few minutes, that what should be true is that physically, we have event horizons. In fact, I can go find them, right? And say, the singularity is inside the event horizon. I know information cannot propagate out. That's the definition, right, of a black hole. And so I should be able to ignore completely in the inside. People stuffed things in there, just like other solutions to make it better. We've cut them out. It's called excision. The ones I'm going to use here are moving punctures, which means you kind of ignore it and hope for the best. Kind of a weird faith-based, and it works. But you shouldn't care, but the problem is computationally that you do. And so a lot of time and effort is spent if you're going to, is spent in trying to make sure that the non-physical modes that propagate out aren't going to kill you. They're the same order of error as all this other messy junk in here. Hey, look.
This may be a related question, but the metric decomposition that you had,
Mm-hmm.
the 0, 0 terms minus alpha squared
Yeah.
plus beta
Shifts.
I, beta I, right?
Yeah.
The magnitude of the shift vector. That's basically saying you can't shift too much.
Yeah, so,
That must get violated inside the horizon, right?
Right, it
You
can
have
be
to
super-
shift your coordinates. So
Oh,
that
yeah. You can be superluminal.
Fleet, yeah, exactly.
absolutely.
Okay.
You have to. So then it gets fun to imagine, right? So imagine you're saying to yourself, I'm just going to avoid the singularity. There's lots of ways to do it. I can create a coordinate system where I send it to infinity. No problem. I can start stretching so if I'm I'm not very good at drawing, this is where I get in trouble. Let's go back to the diagram I made fun of the other day, the embedding diagram. Anyway, so I have these really steep gradients coming in. They're getting steeper as we go. So you can imagine that what a nice coordinate system looked like out here starts to look very bad in there. That's called coordinate stretching. So I, almost made it a joke like poor Miguel sacrificed his life for the lapse and shift conditions, but it's incredibly challenging because you can't do this because again you've lost resolution, you're going to crash. So somehow that's where the art is. The art is in the gauge conditions and the initial data. Everything else is actually pretty straightforward now. It's figuring out a way that you somehow balance. So when I say resolve the singularity, what I'm saying is I'm not going to have grid stretching so badly that it kills me. That I have to send in enough points that this doesn't kill my calculation. And the only way you find that out is by trial and error.
Do they really run forever? Or are you like logarithmically falling into the singularity like with a tortoise coordinate or something?
No, you're
You
fine.
just pray that it lasts long enough.
You're absolutely fine. Because really what happens with the punctures is that it's almost like excision, and they sit off of a coordinate grid, and actually you don't. The gauge conditions are very good. They don't actually start. You don't lose points in the domain. We don't have to add points or any of that with the slicing we use.
What exactly is the difference between excision and puncture?
Excision would mean that. Let me show you a picture. I had it. This is excision. This is Dennis Palmy's picture. I think it's very pretty. I stole this from Luciano Mazzillo. So you can imagine, like, our grids don't look that simple because it's mesh banded, but imagine you had a uniform grid on the top, and the yellow would be inside the horizon. And so as we said, I could do whatever I want in there, right? Spin it. So I was joking last night to one of the students that this used to be my talks. Literally, how I was solving derivatives on the excision boundary. Because now you don't have any points inside the black region. Oh, God. Anyway, so I should be able to totally ignore and therefore throw away the singularity because there's no information in here that I care about. And so excision means I literally do not add grid points there. I ignore it, and in my domain it doesn't exist. Punctures means it exists. I'm going to create a condition where I get rid of most of it in a clever coordinate choice, and I'm going to let it, to some extent, sit there. But you make a coordinate choice in which you are hiding most of the problems that you can solve analytically. So you solve as much analytically as possible, and then you just throw a lot of resolution at it. This sounds better. Like I did this for decades because I just like the thought of it. But it creates, and people still do excision, but it creates a lot of problems here at the boundary because you still have to make decisions computationally. You have a lot of one-sided derivatives, and while physically everything's going in and nothing's coming out, computationally you have to ensure that happens, which is not trivial. And puncture coordinates, I'm actually not good at puncture coordinates, to tell you the truth. You never learn anything as well as when you're a grad student, and I did excision as a graduate student, so I'm still always a little off about my description of puncture coordinates. It's kind of funny. But puncture coordinates means this is that stretching I was doing, this is the singularity. In some sense, you're just sort of like never quite getting to that singularity. You got to use a lot of resolution. All right. I know that's the fun part, isn't it? The singularity. This is kind of boring.
And if you send the singularity to infinity, is that also puncture?
No, I don't know if anyone actually does that anymore. It's not, what is tortoise coordinates? Do you remember?
Yeah.
I'll come back. You go.
I mean, you can set up a set of coordinates where, in some sense, if you never reach the singularity, even just these tortoise coordinates.
Yeah.
The trick here, you could ask, why are you doing it? The beauty of GR is it's four-dimensional, and you're taking on, you're doing this, no,
go ahead.
It's old-timey thinking, this 3 + 1 split.
It's very old.
And make it into old physics. Why would you do that? Just solve the 4D. That's what makes GR so beautiful. You should do it in 4D. We don't really know how to do that, so we're stuck doing it this way. But we are. Deidre is taking advantage of all of relativity. We get to decide what we mean by space and time, and all this stuff is the details of what's space and what's time. what is a slice of time? What do we mean by, 3 o'clock? It's completely different depending on what slice of nature.
So you can do all these tricks. I can send it to infinity. I can do whatever I want. There's always a price to be paid. So it just depends on what's the best decision computationally to pay the price. And so you can make all these decisions. The truth is, shockingly, I have to say the moving puncture is the easiest. It's just for some reason the most computationally robust, I think, at this point in time. But it would be great. And people have tried to be very clever. You even doing finite differencing, like the dumbest, I shouldn't say that, I forgot we're being recorded again. There's nothing, it's not very sophisticated even at the finite differencing level, which is kind of annoying. And people have tried to be clever, like doing implicit methods, inverse problems, tons of things. But the truth is, even the brute force approach is really pushing our boundaries of what we can do computationally. And so it's hard to play. It's much easier now that we can actually solve an equation correctly, so we know what we're aiming for. But it's still, when you are talking about weeks to solve one equation, it's really hard to go ahead and say, all right, now I'm going to do this a completely different way in 4D, and I'm going to or do a different approach. So it's challenging to play in this world. And unfortunately, I think now, with the advent of the reality of gravitational wave detection, it's getting harder to only do that and not actually be producing gravitational waves. Yeah?
But so my impression is a lot of this is, it's almost experimental, like you just try different things. You try different things.
It's a combo, yeah.
We'll ignore this part of the solution and hope it kind of works out, or we'll correct it with the constraint. And then you kind of stumble around and some things seem to work, and now there's kind of a general convergence of methods where different methods. But it's not that there's some profound theory underneath it that says this gauge condition is stable, we can show it mathematically.
You can, after the fact. So I'm a little bit cynical about this because I spent a long time, when we were failing for many years, in the early 2000s, basically people came in and said, all right, numerical relativity people, you don't understand what you're doing. We're going to come in and we're going to fix it by being mathematically sound. And, and it just didn't work out that well because the truth is you're using a computer, right? So you can make it as mathematically beautiful if you want. That doesn't mean when you solve it numerically it's going to work out. So it's a combination of when we switch from ADM to BSSN, you can show that is mathematically a well-posed, more like a wave equation with all the probabilities of hyperbolicity to help you, but you can't get away from a little bit of engineering. And I don't think it should be embarrassing. The truth is computational methods, some sense, are a little more like experiment than pure theory, because you're going to have to get your hands dirty and find out what happens when you solve a derivative on a computer, or discrete test.
Do you feel the mathematicians did contribute for significantly? Are there particular things they really helped us in one way or another?
Where's Tiglio when I need him? My office mate and I used to have huge battles. But I feel like they slowed us down for a long time, actually. It wasn't a good place. But now I feel like, in retrospect, looking back, it was nice to have all those statements in place. But we still fall under this spell, which drives me a little bit nuts, that for some reason we should be having this infinitely resolved waveform when LIGO can only do so much. So I'm practical, right? I'm not a mathematician. So I'm like, why would you want me to spend 3 months getting a waveform out where my errors would be so tiny you would never see them in the detector? I want to know, what's the messiest one I can give you where I don't mess up and give you as many as I possibly can?
Could you see Lisa though? What about Lisa?
Oh, sure. Anytime your detector gets better, you're going to have to improve, right? And I'm fully for that. I just don't think we should be insane about this. And I felt for a while that we were, people were asking us to be mathematicians instead of what I think we need to be astrophysicists at the end of the day. Yes.
Is there any advantage of moving meshes?
We do move meshes. Meshes follow the black holes. So these things, when I put a little grid on them, they move around. And then they merge together. They follow.
But what happens when they're moving very
well, they still only move, the black holes tend to be moving at 60% of the speed of light. Sorry. I think that happens. It's all relative. It's okay. We can define it to be anything we want. Ilya and Antina.
So, I mean, obviously you have lots of...
I didn't know you guys had so much
tools to-
deep-seated NR stuff.
Yeah, it's more of a historical question, right?
Okay.
So obviously, you know, there are lots of things that people have been playing with for many years. How you do the meshes and the adaptive measure filing, the meshes, how you specify the gauge, how you specify the space-time splicing, what kind of boundary condition you pick, constraint-preserving boundary conditions, and so on and so forth, right? How you choose to discretize your equations so that you suppress constraint violating modes, etc. What out of all of these things, right? Did you really need all of them in order to finally have the breakthrough, or is there sort of one particular one that was responsible, let's say, for France's breakthrough in 2005 and everybody else's successes that followed?
So I think and it's been a while, it's 2005. Actually, it was a funny story because we were in, where were we? We were in Canada, we were in Banff. And if you know Matt Chaptuik, he's funny, but he's not a guy to call the press in. And we were sitting, and all of a sudden cameras show up, we're like, Matt, what are you doing? Anyway. So with Franz, because since he did everything sort of lone wolfish, but with a lot of contributions from other people, I would say for him, he had the best mesh refinement. Wrote it with Matt. Matt was famous for being able to do these beautiful mesh refinement, and he had these constraint satisfying, work with David Garfinkel and Carson Gunlock, which really gave him control of the errors propagating in his domain, and he was successful using that. But he was also not influenced by the historic facts, which I think helped him greatly. By being a person who was willing to just write his own code and ignore what everyone had done and pick and choose things that were very good, it was a very controlled experiment. And the second he could do it, it only took us, well, I guess it took the people, we in my group were not doing any of these things. We had a completely different setup. So RIT, which is now, what used to be Brownsville is now RIT, and NASA were already using a lot of the work that the then AEI group under Ed Seidel had developed. So they were the group that had almost everything. If you looked at their old code and their equations, it would look almost identical to what we all use now, but just hadn't come up with the right combination of gauge. They had some very small differences, one parameter different, and mesh refinement. And so that was luck, right? Pedro Marinetti happens to be visiting Carlos Emanuel and says, hey, have you ever tried turning that parameter off and letting this thing just move around? And it would prevent some of the grid stretching. And Dale Choi at NASA decided to explore, and he gets it right. So those two people do it at the same time. A month later, we could rewrite our entire code. That's how simple that approach was. So there was nothing too profound in that one. I think Franz wanted a little bit more because he really was the one that said, you have to know, and this is Matt's training, everything that's happening in your domain. So he was more controlling everything. But after that, you've all realized that once someone can solve the problem, everyone solves the problem. It's easier. So it's hard to diagnose exactly, like if I took pieces away, but you have to, it's all about keeping the computational errors, these discretization, non-physical modes from killing you. Whether you damp them or you come up with good solutions that don't generate them in the first place. These are not student questions, I'm kidding. Want some E&M? Does that look like electromagnetism? Probably doesn't, actually. But this is what would happen if we took Maxwell's equations and wrote them in 3+1. It would look the same. So you'd have you would have 3 constraint equations just like we do, and you would have these 2 evolution equations. So oftentimes in general relativity, we'll invoke electromagnetism to give you some intuition. It has similar problems, computationally speaking, because you still have to get the radiation out. And this is the way the equations would look. You can see that they're not as complicated, so they're not as hard to solve, but they have some similar properties. And so if you are confused by what I wrote on the one slide, now you can look at this and say, oh, okay. So the left-hand sides here, the vector potential is kind of like our spatial metric. The electric field is kind of like our extrinsic curvature, et cetera, and its role in these equations, if that helps you kind of think through it. All right, so I already said that. Sorry for all the words. And at some point I had all the citations. Sorry, I have to go back and put more of them in. And simplifying the slides, I lost some of those. But so we don't use this because it is not well posed, which means it allows small perturbations to grow without bound, which is, of course, a bad idea. So a lot of the things that people were asking was exactly that. How do you get handles on these attempts to keep things from growing? The most popular thing is the Shibata Nakamura Baumgart-Shapiro thing we already talked about. And the thing to keep in mind is that even the number of equations you're solving depends on what formulation and gauge conditions you've written down. So I couldn't even tell you how many equations our code solves, because it kind of depends on which approach we're taking. But it's about 17 evolution equations, which are nonlinear PDEs. And it's always 4 constraint elliptic equations. So BSSN makes different choices again. You have this ability to change the way you define everything and attempt to keep small perturbations from growing. So, there's entire Bibles about this in computational theory long before you ever get to general relativity. So you can do a lot of tricks. Here are some of them that would take you from ADM to BSSN. And I don't think it's important in this group to talk about that. I just wanted you to be aware that there's a lot of different ways you can write this down. And there's more formulations than this. This is just the most popular. But there's tons of them out there that work. So this in the end is an initial value problem. So the real hard part at this point is to specify everything at the initial time and then solve it. So determining the set of physical conditions that represents the plausible configuration is the part where we spend our most time now. And then you solve the equations to represent those solutions. So the thing that's most important these days is this part. Now I'm all for, in fact I would love to have somebody who is really just in it to improve the speed of the code, or in it to make it look like we don't live in 1960s finite differency land, but we do what we can. So here are the constraints. Again, this is how we're going to specify our initial data. Specify the initial data, we get to have too much freedom again. So general relativity is always a problem of too much freedom. And so in this world, we have to make decisions and hope that those decisions lead to what the universe would actually give us when you collide 2 black holes. So we have 4 equations and 12 variables. That's where the problems come in, right? That's a lot of freedom. It's like being a teenager again. Your parents are out of town. So we have to define all those things. So that's the art of numeric relativity, is the freedom to choose that. Now, I think we do something that I understand why we do it, because it makes the code solving better, but it gives us a lot of problems. So actually, a large majority, not everybody, but a large majority of people use 2-puncture code, which was written by Marcus Ansorg. And this allows us to solve initial data, solve elliptic equations on a set of a domain with 2 holes in it, which is really hard. Everything that's hard about this is because there's 2 holes in your domain where those singularities are. So Marcus Ansorg wrote that code that a lot of us use. In doing it, he had to make a conformal transformation, which means that you basically choose coordinates that makes your metric look flat, with a condition out front that actually holds the fact that you have 2 black holes there. But the consequences of that are kind of strong. One of the consequences of that is that I can make my black holes initially spin as fast as the Kerr limit, but the second I solve the equations, they lower their spin. So using this type of initial data, I can't do maximally spinning Kerr black holes. I can get high, like 0.95 of it. But that conformal flat decision, which makes solving this so much easier, adds more junk radiation into my domain, which means the black holes absorb some energy, they get more massive, and therefore they're spinning less. The other consequence of all the initial data is that we don't have any gravitational wave content from what the black holes have been doing for, a million years before we got there. So we're basically starting as if they start there all of a sudden. So this is what we call junk radiation, and if you look at, you never see it, but if you looked at our real output, it would look, and then we would start the gravitational wave. And for a long, the truth is, though, that this flushes, this is the junk, this is the non-physical stuff that's there because of some choices we've made. And this looks bad, but it would look like gravitational wave. But these, we just remove it, and we haven't found any problems with it contaminating the gravitational wave itself. As Cole asked, the better our detectors get at detecting gravitational waves, the better we're going to have to be to make sure that these types of things aren't influencing our solution. But for the most part, it just flushes out of the system, and we can mostly ignore it. But that's one of the dirty secrets, right? Our choice of initial data do change the quality of the gravitational waveform, not just in the physics of what we're representing, but in non-physical things that can float around and that we just chop off before we show it to you. Right? We're not stupid. Okay. So we already talked about this quite a bit. Oh, I said shutter. I hope I spelled it right. Because, they're just such a pain. Gauges are a pain. So we already talked about this, the lapse and shift. We talked about two punctures and excision. But the way you actually, so I talked about excision being you can cut a hole in your grid. The way you implement the boundary conditions of that decision, and the way you do this kind of like fancy, what I call the faith-based method of two punctures, is that you make decisions about the lapse and the shift. So everything's coming in from some of these decisions on the lapse and the shift. So the way we actually solve those equations is solve them as PDEs. So when I joke that we don't know what our coordinates are at any given moment, it's because we're solving evolution equations for their coordinates. Okay? So there's no analytic expression. I can tell you what it looks like. It might look like some physically sound, minimal distortion or something. It's based on something physically we want to achieve. But in reality, we're solving it. I spelled singularity wrong, which is very embarrassing. But in reality, we're solving equations to dynamically control. If you try to make this once, the reason why these grid points aren't going away and we're not suffering is because we're doing this at every time step. We're adjusting the situation so that everything's still doing its job. So here we are in a space-time diagram. This is our singularity. Here's that black hole horizon, and that's that gravitational wave. And so we're making choices so that we ensure that we can kind of ignore that singularity. Because what they look like. One choice. Everybody's looks different. But one choice of gauge conditions would look like that. So there's our time derivatives of the lapse and the shift, and that was really a second order PDE, and we rewrote it as a first order. And all the horror comes in from choosing lots of these little variables and parameters, and you can adjust them and pick them. So you can imagine what an experimental nightmare that is, because one choice could make it work and one choice could not make it work. So that's where a lot of problems get in for people. So, but I left finally one citation in of ones that are the most modifications of this are very widely used. All right, there's something else I hadn't told you. Oh, we're still going fine. I kind of sped up there for a second, sorry. So I've been talking a lot about the gravitational wave extraction because at the end of the day, what we want is to provide all these representations of gravitational waves. And so we have to somehow get that out of the code. And furthermore, we don't actually deal with strain. We deal with something called the Weil tensor, just more stuff. But what we have to do is we have to have something that we can build from the curvature tensor, and something that's going to really be coordinate independent. It always has to be coordinate independent, right? Otherwise, mine is going to look different than somebody else's. It's going to look different than the inverse. That's no good. So I didn't bother explaining what this psi4 is, but if you hear numerical, we say psi4 a lot because that's what our code produces. So when you look at something like this, pretty picture, or you guys have a picture of gravitational waves on the front page of your brochure for this little school. This is gravitational radiation coming out from the merger of two black holes. So if you're sitting inside of our computational domain, gravitational waves are everywhere, right? You're like sitting in a big sea of space and time, gravitational waves propagating out. Then why does it look like this when we plot it, right? That's because we've chosen a line of sight, and we're basically plotting along a line of sight the in-spiral signature of these two black holes, right? So this is what we solve everywhere in space and time. We solve for what will be gravitational radiation at Scry if you go far enough away. So that's the decision we have to make. We have this at every grid point, this information called psi4, which will eventually be gravitational radiation, and then we have to get it out of the code and make it into something that will eventually become strain. And so we basically take a bunch of circles, a bunch of spheres, and extract the gravitational radiation on that. So there's more numerics there. There's more decisions about how you interpolate. So there's also errors that can arise from those decisions. But then what we do is we take two time derivatives, two time integrals of psi4 to give you back strain. Psi4 is a complex number, so we have enough information to get plus and cross. But that, again, is another art form, because I have it somewhere. It's another art form because when you do this integration, if you integrate once, you get a little, a little shift. You integrate twice, you get this drift. So you guys heard of the memory effect? Mark Favato loves memory. It means that there's some imprint left in the space-time after from the gravitational waves. But when we do decisions numerically about making strain, we pin our boundary down, so we kind of erase it. So we have to make decisions because we have to integrate Psi4 to get strain that could also have an impact on the gravitational waves. So these are all the places where we make decisions that are not physical in nature. And so creating HET can also cause problems. We don't know what the coefficient should be when you solve this integration, so we have to just do the best we can. And what most people do is the Pauli-Reiswig approach that integrates everything in the frequency domain and comes back. But still, it's just something to keep an eye on, that it can also cause little issues. The other thing we should mention,
Net plot was at side 4.
in this one,
Before
this is strain now, this is Psi4.
Okay.
You couldn't tell.
If you go back to another slide, that relation, relating side 4 to the strain,
Mm-hmm.
does that hold as scry or everywhere?
Well, you can do this. This is true everywhere, but you have to make sure you extrapolate to infinity. So what we should give you is an extrapolation to infinity, and we would do that in Psi4 first and then create strain.
So there's a notion of strain close to the binary.
I see what you're saying. Mathematically, I don't have a problem doing it, but it's really a description far away of what's happening.
So does it make sense to ask what is the value of strain close to the binary?
You absolutely can ask that. What we tell people, right, when we joke and give public lectures, is that it's so weak when you're at Earth. But of course, if you're near the binary, you are going to feel some effects. But to call it outgoing gravitational radiation mathematically, Psi4 gives you that at infinity, properly, definition of it.
So would you be able to say whether you could be close enough that you could actually hear the gravitational wave?
Its amplitude would be large enough
Yeah.
if you converted it to... I think you can make that statement. How physically realistic it is a different story, but... Dan, you went away and Will, I can feel them itching back there.
There's a near field, far field thing.
Yeah.
Yes.
What you're talking about. So you're asking a near field question? And it's, what you really want is some problem.
The far field.
But you only really want to find in this far field way. So,
And
there
that
will
time
be,
strain is much less than 1 by definition because R is much greater than the characteristic size of your source.
Yeah.
So there's no way to have pure unit offsets.
well, but there will be huge tidal effects.
That's the thing. There are physical effects.
And
That's all.
those physical effects will be changing with time. And
You can hear it.
in principle, hear that. There'll be other issues too. But
We won't call it H.
but you wouldn't call that a gravitational wave.
Yeah.
That's just time changing time.
It will hurt. I have done the calculation that how close would you have had to been to GW 590914 to rip apart. But to do it, I fake it because you look at delta L over L, which is really H, which is really not what's happening. But anyway, you can play these games, but it's not really gravitational radiation.
So what is the standard test for the code that everyone wants to reproduce?
So one of the first test everybody does is because we are actually solving a problem where there is a solution, right? So we're just discretizing the equation. So if we did infinite resolution, we should recover the continuum solution so we can use convergence tests. So we do convergence tests, which means you more and more refine your grid, and your solution in this case, maybe it's this, right? There's some caveats to that, because this is not solved at every grid point.
Yeah.
But, so you would start with looking at your actual variables. Do you converge to this solution? And then the reason why it's not so simple is because first off, you don't have a uniform grid, and then to actually get the physical thing we're providing for people, we've done some other things like interpolate on the sphere to call this outgoing radiation. So there's other things that mess that up, but in principle, the building block is convergence.
But is there a tolerance to say, like, I'm within 10 to the minus 3 of the continuous solution, or
So, no, right? There's not like, so what is the continuous solution? We don't have a solution, right? There isn't an analytic solution. There's only comparison to better and better resolution. So what you can do is put uncertainties on top of your waveforms to say, how are you changing? And you had better be changing at the order of your choices numerically or finite differencing, whatever order your truncation error is. So you can do that. You can also do, that's why we also compare with each other. We do a lot of that. Because then we've made different decisions. It's almost like replacing out your evolution equations with a different technique, and you should come up with the same answer. Because there's no analytic solution to compare to. So that's why we're constrained to looking at more and more highly resolved solutions.
at a large distance you can do positive something.
Absolutely. So if you're black holes, so by large distances what we mean is that when the black holes are far enough apart, both post-Newtonian and numerical relativity should recover the same gravitational waveform. So those tests are also done. And what's the only problem there is the best tests for that are done by the SXS group because they can evolve the black holes the furthest apart. Because the problem is that post-Newtonian is breaking down. So if you look at what's happening when we make comparisons with post-Newtonian, there's different choices in how you do the post-Newtonian, and those errors will actually be bigger than ours at some point. And that's when we call ourselves, all right, from NR standpoint, we've done what we can. Well, Dan was first, then well.
I just on that, so people used to do Misner data as kind of a nice test.
Yeah, we did a lot of things like that in the beginning on the codes. It's true we don't do much of it anymore because the codes are old. But yeah, you could do Misner, you could do wormhole, all sorts of fun little
Just as
bridges.
Tell us what you have. Pretty good analytic
Do cosmology tests. We used to do that too, just to prove that we could evolve forever, and not rise things. Yeah, so I forget, that was like 20 years ago. Boy, maybe we should go back.
But just in a sort of so is the message that the initial value problem, sort of initial data, that's more or less under control? That the issues now are more, propagation on meshes and boundary conditions, more dynamical issues?
I think it depends on what you ask. For something we all can solve, like if you ask me to solve GW5914, which is easy because they don't look like they're spinning very much, then the bigger issues are all in the meshes, blah, blah, blah. If we wanted to curve black holes, like maximally curve, this initial data can't do it. And so, Jeffrey Lovelace, a lot of people have been banging on that, how high can we actually spin these black holes up? And that's an issue because we don't have robust initial data that can handle that. So if we're talking about highly spinning black holes, our initial data is the problem. If you're talking about bigger mass ratios, so right now we've done about 15-to-1, 20-to-1 in my group. RIT's done 100-to-1, but without getting gravitational radiation out. Then our problem is that we can't resolve the smallest black hole. So the tension is that the only scale in numerical relativity binary black hole work is the black hole. There's no other scale, right? That's why these things don't look messy. They don't look like turbulent, shocky, because we have a black hole. It's our smallest scale. So if you have two black holes, your smallest scale is the tiny black hole. And so your resolution is dependent on how well you can resolve the itty-bitty one. So that drives up the cost of the computation, which kills us. And there, it's not an initial data problem. It's how the heck. So we could have also tested with perturbation theory, which is where you take a black hole solution and you perturb it by the second one, but we can't get to those extreme mass ratios. And I don't see a path forward without someone coming up with a different way of doing numerical relativity to get that. So those are those two extremes. And then the middle extreme is if you want to spin and mass ratio, like higher spinning also needs more resolution because as black hole spins, they get a little oblate. So it just causes you to have high resolution. The other problem we face that I haven't mentioned, which is another kind of initial data problem, is that when I have my two black holes and I want to get out gravitational radiation and I have to pick my spin vectors, we can have precession, right? So that means that the orbital plane can be moving in time. As it merges, it just does that. But anyway, it can be moving in time, and the spins, they're moving, right? As you orbit, they're changing direction. So it's really hard to say, I'm in numerical relativity, I started with my spins in a certain direction, I've produced this wave. Now, what did my friend Harold Pfeiffer do? He picked something, but how do we say those two runs are the same? Or even compared to Poisson-Tonian, because the spins are changing in time. So you might pick a gravitational wave frequency and say, all right, we all agree what our spin vectors are doing at this moment in frequency and compare, but it's really hard to set up initial data to do these comparisons, which is what we're doing right now. And this is where we're spending, you won't believe how much time graduate student life goes into something that, like, at the end of the day, you're not going to talk about, but trying to get two people who have different initial data to say, these are the spin vectors I started with. When I solve my initial data, it's changed. And so it's not, this is where it's like, a little finicky. So that's part where I'm struggling right now would be that. Because we want to give everyone all these processing signals, but we have to figure out, got to do our homework first. So it's a bit of a pain. So, I mean, people say it's a solved problem. It kind of is. It's just that it's annoying now, actually. You died, little baby, didn't you? You're like, whatever, you've ignored me too long. So another thing I was going to talk about today is that we also do, when we plot this, if you actually notice what we're plotting, and, it's going to be called, it's going to be time, right? My units are non-existent, as Cole will tell you, right? I'm lazy. The reason why my units don't exist is because I don't have any units. My unit is the scale of the black hole mass. I have no physical units. So I solve one gravitational waveform for a specific set of physical parameters. I can make that be a 10 solar mass black hole binary or a billion solar mass black hole. I just multiply, right? So there's no reason for me to have units of seconds and things like that because I just multiply. 5 microseconds per solar mass. It's the only unit I remember. Just give you. So when we plot these, though, we have plotted only one mode usually. Well, this is cycler, right? So this is what we mean by that. So right now you hear us all talking about higher harmonics, higher modes, blah, 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 and this is what we're talking about. So we've already listened to Cole talking about the fact that gravitational radiation comes in at quadrupolar, right? That means L equals 2. So what we're doing here is usually when you're in an in spiral, your dominant is L equals 2, M equals 2. If we're doing head-on, we'd have L equals 2, M equals 0. So what we've done is we've extracted this gravitational radiation, which is on a grid. We took a sphere that we take a bunch of them so we can extrapolate to infinity, so we can call it gravitational radiation. We've done that on an angular grid. And then we use spin-weighted -2 spherical harmonics, which are a lot like your normal spherical harmonics from like quantum mechanics. And we start pulling out the modes. So you can get the fundamental one, 2, 2, and that's the one you always see. So GW 150914 doesn't really have any other modes because he was pretty much almost, kind of non-spinning-ish, right? He's consistent with non-spinning initially. And that, all the power goes into the 2, 2. The higher the mass ratio between the two black holes and the more processing the spins, the more gravitational energy is radiated in the other modes. So that becomes a different problem that I'll let Will solve. So that's challenging. Anything else I want to tell you about? I thought this could be fun. Yes, sir?
So if you have psi4, why is it hard to extract the higher modes if you already...
Oh, it's not. Numerical relativity has them. Now, the quality of them will go down because as their frequency increases, at some point we won't have resolved them all enough. So one of the answers to, as our detectors get better, we will have to do better at getting all the modes. So, there's job security in some sense, I guess, but it's kind of boring, just resolving it better. But the hard part is that when you're detecting these things, the more information you put in that model you're using detection, the more likely it's going to look like every noise source out there. So you don't want to just throw everything in it. It's going to look... So it really is... That's why I said Will do it, because he does the proper data analysis. And I'm like, use everything. And they're like, go away. That's not helpful. So you have to make choices that are sensible. And that's really coming from the detector side. We're only worried about, for example, if there's missing... You don't want to miss physics. You don't want to miss a source. It's unlikely that you wouldn't detect something because you don't have these higher harmonics unless it was like a really strongly precessing or really inclined orbit. How inclined is that orbit compared to you? So there's reasons why we don't go after all of it. It's not laziness. The other thing I wanted to mention for fun, because I did this a lot as a student, was at horizons. Because what we do not use are event horizons. In fact, I'm sorry, every time I see an astronomy picture in like CNN and they say, the event horizon, can't see the event horizon. The event horizon is a bugger because he's defined, again, at infinity. And you have to know the entire evolution of the history of the universe and go backwards in time and figure out what was the boundary between things that reached infinity or didn't. If nothing else interferes with that space-time, that black hole, then you know it, right? Because it's not going to change in time, and you can figure out where the event horizon is. But we don't use the event horizon in numerical relativity because we have a spatial slice, and we need to understand where is our measure of the singularity, where is the horizon on a spatial slice. So this is goofy, but because I couldn't find the original Penrose diagrams. But if you imagine a collapsing star, you can imagine that if you waited and came back afterwards and looked for that boundary of what escapes infinity and what doesn't, you could draw that blue line, which would eventually be these spheres that don't change in time and space. And that's your event horizon. Oh, he's so little. He's so cute. So if you, my drawing is fantastic, right? I do better actually drawing on my iPad than the board. But if I have a shell of matter that comes in later, then the event horizon is going to grow. So I would have gotten it wrong. So what we need is a way of describing where the horizon is on time slices, in spatial slices, and that's called the apparent horizon. It's not the best thing because it's gauge dependent, so it's not always there. But if you can find it, it's guaranteed to exist inside the event horizon. So here is now the event horizon, this red thing, because something fell into the black hole and it grew. And the apparent horizon is this. See that where that is? Because it's always the outermost trapped surface, and this is the trapped surface, this isn't yet. And now here, this would be the apparent horizon. So at every moment in time, all we have to do is look for where light neither converges or contracts or expands, and we can get a measure that is guaranteed to be inside the event horizon. That's all we care about, because we just need to be inside of it. So we don't remove any physics if you're going to do excision, or if you were just going to locate the black holes. So I just think things like that are these subtleties that we don't talk about. Things like where is the apparent horizon. So I just wanted to bring it up. So if you, yeah.
So can you use these to probe the amount of gravitational rotation that bounces back?
So this is again a near field far field problem, and I love these problems. So one of the questions would be, a black hole, you have imagining that this black hole, call it a single black hole now, it's just merged and it's ringing down, and we know what that radiation looks like infinity. Could you understand the near field consequences on the horizon? It's really the potential, which we don't know what the potential barrier, the potential is. But could you understand it? Abhay Ashtekar has worked on these things. So he's developed a framework called isolated and dynamical horizons, which try to relate near field and far field quantities. But it's not, you have to do a lot. Because first off, if this apparent horizon is dynamical, it's gauge dependent, so you got to be careful. But if you measure, can you measure the mass and momentum flux through the horizon and make statements is really tricky because things really are defined in the far field region. But people, Abhay's trying. It could be interesting, we'll say. I actually tried to find the potential that's forming around the two black holes, but we couldn't find it. It's really hard. Because if you think about it, not only are these two black holes coming together, they have their horizons, but outside of that is this. Have you guys ever studied a Schwarzschild black hole, studied orbits? And you see that the potential is like outside the horizon. So you can imagine that this big potential barrier is forming somehow outside these black holes and defining what escapes and what doesn't. But can't. It's really hard numerically. This is what they look like. I just think that's pretty. This is the event horizons from an unequal mass that Bernd Brueggemann's group did. We don't usually plot the event horizons, but if you did, it would look something like this. It's very pretty. Because it's shiny. Everyone knows that event horizons are red and shiny. I like them. I shouldn't do that, so I'm going to skip it. But, so one of the things that we have to remember, I'll skip talking radiation. So when we do these types of things, the trick is, right, that we're radiating angular momentum, we're radiating energy. We calculate all that. We can calculate all that from Psi 4. So if you get this information out, we know all that in numerical relativity. And All those are outputs. Kicks, all that information is outputted from the code. How the recoil of two buckles. So anything like that, if you guys have questions, you can ask me. Because tomorrow, I was going to focus more on what does this waveform look like and how does it interact with the other waveform models and things like that. So I'll stop there. It's 11:30 almost. Thanks.
Before we wander off.